Okay, so yesterday I concluded the talk by giving you an idea of how you could prove non-intersection probability of two random walks in dimension 4. I hesitated a little bit because I thought that it was a little bit messy and that maybe the best would be to directly go to currents and tell you how you do in currents rather than giving you half the story for random walks and then half the story for currents. It would be a little bit worse. So let's go back to currents. Okay, so remember that we are trying to prove, we are trying to bound the probability. We have 4 currents, and the probability that the cluster in N1%2 of X1 intersects the cluster in N3%4 of X3. We want to estimate the probability that this is non-zero. So this set here, let me call it S, okay? Okay, so we want really to be proving that the probability of S non-zero is small. And we are going to bound this as follows. So we are going to fix a K and say, okay, either S is larger than K, or S is strictly between 0 and K. Okay? Larger or equal to K and strictly. So here, this thing, the first term, the good thing is that we can bound it by this, and this, remember, is exactly the tree diagram bound. Sorry, we can bound it by this divided by 1 over K. This is by Markov inequality. Oh, let me write it like that. So P of S larger or equal to K is smaller than 1 over K time expectation. And this is 1 over K times the sum over X of sigma X1, sigma X4 divided by sigma X1, sigma X2, sigma X3, sigma X4. So this is perfect because these two terms here, they are going to cancel with, let me put it like that. These two terms here are going to cancel with the sigma X1, sigma X2 in the U4 formula. Remember that in U4, we have, we have this term here. So this is perfect. And the top term is exactly, and this sum is exactly giving you the tree bound. So you are improving the tree bound by a factor 1 over K when you do that. And the goal will be to choose K properly, okay? On the other hand, we want to bound the other probability, okay? And in order to bound the other probability, we are going to introduce a definition. We say that X is K. So what was my notation? That just I do something correct. It's KL isolated in S if X belongs to S, and the number of I such that S intersects AI of X. Remember AI of X, maybe let me write it like that, annulus center at X with inner side Ni and outer side Ni plus 1. So Ni plus 1 is Ni squared. So such as this is non-zero, this is strictly smaller than K. Okay? And maybe let me not use K here because it's going to collide with the other notation. Let's call it R. Okay, so this is a definition. It means that there are few annuli around you that intersect S. Okay, and there was this lemma that I mentioned just briefly, but that now I'm going to state, which is the following. It's saying, assume that S does not contain any let's say 5k, k over 5, sorry, I meant r over phi l. And L, this is the number of I small, I such that Ni. No, actually, let's drop the R. So this is just R isolated. So assume that that S does not contain any R over 5 isolated vertex. Then I claim that S is larger than 2 to the R. Okay, that's the lemma. So in order to have small cardinality, you need to have isolated vertices. Okay? Okay, so in order to bound the other term, which is this term, what we are going to do is we are going to say, okay, if you have this, then if we set 2 to the R equal k, if we do that, then we need that there exists X in S, which is R over 5 isolated. Right? Okay, and this you can bound by the sum over X of the probability that X is in S and X is R over 5 isolated in S. Okay? So now, if I can prove that for some R, which is not too small, the probability of being R isolated is small, then I will have that this sum, so now assume for a moment that the probability that X belongs to S and X is R over 5 isolated, assume that this is smaller than epsilon times the probability that X belongs to S. Let's assume that for a moment. If you have that, overall, what you ended up, if you look at this bound and this bound, you end up with the fact that the probability that S is non-zero is smaller than 1 over k plus epsilon times expectation of S, which is giving exactly the diagram bond. So the game is really going to be, can we pick k relatively large, epsilon relatively small, for this to give me something good. Okay? So from now on, what we are going to do is k, we are going to take log L to some small constant. So that tells me that R, which was here, should be something like small constant log L. And we are going to prove that, in fact, for this, epsilon can be chosen as 1 over log L to some small constant. So maybe C0, C1, C2. Okay. Okay, so let's make this choice. And now let's try to prove, well, there is only one thing to prove, which is this thing here. Okay, that's the only thing we need to prove. I mean, together with the lemma, but the lemma, I'm gonna skip the proof. Okay, I don't want to be proving this lemma. It doesn't have, it doesn't refer to the Ising model, as you can see, and it's not very difficult to get. You can try on your own. It's, I mean, actually, I'm pretty sure we didn't do something optimal. Probably there is a way to get rid of this divided by 5 or something like that. I mean, there are probably ways of doing to state a nicer lemma. So what we really need to prove is this, this thing. Okay. So again, the heuristic, why this is true, should be that, oh, okay, no, maybe one first, so let me restate. So this is x1, x2, empty set, x3, x4, empty set, and I want x belongs to C n1 plus n2 of x1, x belongs to C n3 plus n4 of x3, and x is R is basically C1 log L isolated. Right? I just rewrote it this like that. Why did I rewrite this like that? Because here you see that this guy and this guy, you are allowed to use the switching lemma here. Why? Because this being isolated here doesn't depend only on the two first currents, but it does depend only on the sum of the two first current and the sum of the two last. So I let you check that the switching lemma works perfectly well in this context, and you end up with the following. You end up with sigma x, sigma x1, sigma x, sigma x2, sigma x, sigma x3, sigma x, sigma x4, divided by sigma x1, sigma x2, sigma x3, sigma x4, and here, sorry, what is happening? And here you get probability x1x, x2x, x3x, x4x of the same event. I mean, of x is not, is C1 log L isolated. What did I do here? I just switch, I use the red to switch the sources here, and I use the green to switch the sources here. Right? If X is in the cluster of C1, of X1, it means that X is connected to X1, so I can switch XX1, sources XX1. It's just that the switching lemma, remember, is at the level of the partition function in some sense, it's at the Z. So when you rewrite it in terms of probability, you have these additional terms in front. Sorry. Okay. Why is it good? Because you see that this here, this yellow term is exactly actually this guy. So the only thing we need to prove is we need to prove that this is smaller than 1 over log L to some constant C2. That's really what we want to prove. So we are back at the probability. So here we switch. So we use X belongs to S as a way to switch sources and to recenter the sources at X. Okay, so now the goal is really to get this bound. x is C1 log L isolated, it's smaller than 1 over log L to the C2. Okay, so the remainder of the class will be devoted to that. Notice one thing is that, so how does this current looks? I mean, so this measure looks, there are like 4 currents, and all, I mean, the currents are sourceless except that they have at least, so they look like that. This is, say, the first current. Then you have a second current that goes like that. There is a path to x2, and then there are loops. There is a third current that goes to x3, and a fourth that goes to x4. But my point here is that it's not difficult to believe. I mean, you would need to prove it, but you can prove it. It's not very difficult to believe that sources are helping you. Why? Because the more sources, the bigger the currents, so the bigger S, and therefore the smaller the probability that you are isolated. So it's not completely clear. We are not with percolation. We are not, I mean, so proving this regularity is not, I mean, this inequality is not trivial, but believe me that here you can remove 2 sources and put simply sourceless. It's actually a larger probability. So if I can bound this one, I can bound the other one. Okay, so this is not crucial. I don't want to be kind of spending too much time on that. So let me just give you this, this inequality for free. So you can remove 2 sources. So from now on, we are really looking at this. Okay. So as I said, there are 2 ingredients in the proof. The first ingredient is going to be that the probability xx1 empty set, xx3 empty set. Let's assume that x1 and x3 are at distance L, maybe L over 2 of x. Notice, remember that the xi were at distance L of each other. So that doesn't mean they are at distance L of x. But here, when I remove the sources, I could remove either the sources xx2 or the sources xx1. So I could always choose to remove the sources for the xi, which is the closest to x. So I can guarantee that x1 and x3, without loss of generality, are at a distance L over 2 of x. Okay, so I'm going to assume that for it. So first thing is, okay, if you have x1 and x3 at distance L over 2 of x, then the probability that C n1% 2 of x intersects C of n3% 4 of x in the annulus x ni plus 1, this is positive as long as ni plus 1 is smaller than L over 2, maybe even L over 4. Okay, so as long as you are before, so you have x1 and you have x3, and you have x, as long as you are looking at annuli in the middle, ni plus 1, then the currents, the 2 clusters, they intersect with positive probability. Okay? That will be the first ingredient. And the second ingredient will be a mixing property. So the mixing property will tell you for any event E depending on lambda ne of x, and any event f depending on, let's say, lambda, I mean, the complement of lambda and E plus 1 of X. Okay, so I take one event that depends on this area and one event that depends on this area. Then I claim that the probability, of E intersected with F is larger or equal to the probability, minus the probability of E, probability of F. I claim that this is smaller than 1 over log Ni. I could even put Ni plus 1 over Ni to a power C. I claim this. Okay? Okay. Is it clear for everybody that if you have these two things, then you end up automatically with the fact that the probability of X being C1 log L isolated for some C1 very small, that this is smaller than 1 over log L to the C2? It's simply, you have positive probability of intersecting in the first annulus, okay? And then what you do is that just you say, okay, maybe I do not intersect, but on the event that I do not intersect, by the mixing property, I'm going to intersect, so maybe not in the second annulus, but in the third annulus with positive probability. Then if I didn't intersect on first and second, then I still have positive probability of intersecting on the fifth one. And this, by applying just a very simple argument, you very quickly end up with the fact that, in fact, the probability of intersecting in few annuli has very small probability. This is really, think of it as basically telling you, 2 is basically telling you that you have mixing between different scales. It's kind of an additive mixing, but it's sufficiently good that you end up with the fact that you are isolated with small probability. This is really like a small exercise. So the 2 key things that I need to convince you of is the fact that you intersect in annuli with positive probability and the fact that you mix. Okay? So first lemma, I'm going to recenter everything. So X is going to be 0, and X1 and X2, I'm going to call X1 and X3, I'm going to call them X and Y. So I'm going to prove that for every N, there exists a C, such that for every capital N larger than N to the 1 plus C, actually for every C it works. No, for every C, there exists a delta, which is a delta of C, positive, such that for every capital N larger than N to the 1 plus C, I get that the probability, the probability 0x empty set, 0y empty set of Cn1 plus n2 of 0 intersected Cn3 plus n4 of 0 intersected with the annulus small n capital N, this is larger than delta for every x and y, not in lambda, maybe let's call 2n. Okay? So that's the first property, just written in a more generic fashion and with lighter notations. How do we prove that? So notice that this is really something for random walks, which is also fairly easy to prove in dimension 4. And notice that it's very important here that the scales are going like that, right? It's not dyadic scales. They are blowing up. Okay. So how do we prove that? Well, let's call M just the intersection, the size of the intersection. Okay, or maybe let's call M the set. It's going to be a little bit simpler. M is this set. So that's the definition. So I'm going to do a second moment. So I'm going to look at first the expected size of M. Okay? So expected size of M is going to be the sum for U in the annulus of the probability that U belongs, U is connected to 0 times the probability that U is connected to 0. You agree? For U to belong to M, it needs to be connected in N1 plus N2 to 0, and it needs to be connected in N3 plus N4 to 0, but these two sums of currents are independent, so the probability is just the product of the probabilities, okay? But notice that here, it's fairly simple to estimate the quantities. It's sigma 0, sigma U, sigma x divided by sigma 0, sigma x, and the second term looks the same with y. Sorry. Now, when I plug my regularity assumption, when I use the fact that you are up to constant of the order of the green function, you notice that this thing basically cancels with this thing. Why? Because you remember that x and y are not in lambda 2n. So that means that x is roughly at the same distance of u than it is of 0. Okay? So these two things cancel, and same thing, these two things cancel up to constant. So that means that this expectation is larger than the constant times the sum over u of sigma 0, sigma u squared, which is like log capital N over small n. Okay? Now, I need to bound the second moment from above. So from above, I end up with something very similar where I'm going to have U and V this time. And here, I'm going to have U and V are connected to 0. And same thing with the second measure, U and V connected to 0. Right? That's what you are going to end up when you compute the second moment. By the way, it's an equality at this stage. Okay. So here, you need to estimate not only the probability that one point is connected to 0 in the sum of two currents, but the probability that 2 points are connected to 0. And this, it happens to be, we looked at it, and it happens to be that you can prove the following quite nice formula, I would say, which is that this is smaller than sigma 0, sigma u, sigma u, sigma v, sigma x, divided by sigma 0, sigma x, plus the same thing when you invert v and u. So it's kind of a random walk type bound. If you want to visit u and v, you kind of need to go to u, then to v, and then to x, or you need to go to v, then to u, then to x. Okay? Of course, I mean, it's just a very, it's just for you to remember the inequality, but I mean, it doesn't have a random walk proof. I mean, it's not, the proof is not going like that. The proof of this, I'm not going to do. Okay? You have to believe me that you have such a bound. For people who like the BFS random walks or the backbones, this is a trivial inequality. If you want the backbone or the walk to visit n points, then you need to go one by one. And there should be y in the second term. Yes, you're right. No. For now, I mean, it's only one x here. Okay, so here there is a y, but You see, here I'm just bounding this guy. So there is no y in the second term. Yeah. Okay. So what I was saying is that if you look at the BFS random walk, the probability that these walks, or if you look at the random walk, or if you look at the self-forwarding walk, the probability that the walk is visiting two endpoints, endpoints, is the sum over the different ordering of the probability that you go to see the first one, then the second, then the third, etc. And then you have a decorrelation that tells you, well, then it's smaller than the probability that you go from the first to the second, then times the probability that you go from the second to the third, etc., etc. So here it's kind of an equivalent, but for sum of currents. And surprisingly enough, we do not manage to get it for endpoints. We have it for 2 points, but not for endpoints. Okay, so, and this would be very nice to have an inequality for endpoints. So once you use this inequality and you plug it in the second moment, what you end up with, again using the fact that u and v are roughly at the same distance of x and y than 0. So you end up with the fact that this term cancel. And roughly speaking, you are going to end up with twice sum over u of sigma 0, sigma u, times sum over v of sigma v, sigma u. And here I have squares because I pick one such guy for each one of the two terms. Why is it good? Because this, when you look at it, you can bound it by constant. This guy is going to give you log n. And this guy, then, when you sum this guy, you are going to get log n also. So you get log n squared. So this is where you start to understand normally why on Earth I worked with annuli of size small n and capital N, which is a power of small n. That the lower bounds really involves here capital N divided by small n. While here you only get in the upper bound the capital N. It's actually exactly what makes a second moment fail for dyadic annuli. Because in dyadic annuli, here you still get log n, but here you get small n, which is capital N over 2, so you get an expectation which is order 1, and the second moment which is log n to some power, or the log n squared. But here in our case, because we chose the radii like that, we have that both things are of the order of C log n, both quantities. I mean, one is C log n and the second one is log n squared. So here, we are able to just use Cauchy-Schwarz to tell us that the probability of m non-zero is larger than this log capital N over n squared divided by log capital N squared, so it's larger than constant. Okay? So this is really the reason why you work with this annuli. Just maybe a parenthesis, if you don't have, so it's a remark, without the regularity assumption, what do we do? Well, there, in fact, you can still prove that indeed the expectation of m is larger or equal to constant sum for u in the annulus of sigma 0 sigma u squared, which means it's larger than constant bn of beta minus b small n of beta, right? The bubble diagram. Expectation of m squared, you can still bound by constant times sum over u and v of sigma 0 sigma u squared, sigma u sigma v squared. And this you can bound, you can check. It's bounded by this thing. Let's drop maybe even these two, okay? So here, in the general case of like general, I don't have any information on the speed of decay of the spin-spin correlation. How should I choose the scales? Well, I should choose the scales in such a way that bni plus 1 of beta minus bni of beta should be larger or equal to constant bni of beta. Otherwise, I have no chance to be able to get a second moment method. So it's exactly what we are going to do in general. In fact, we are going to put an equality here. So the scales ni in general are given by bni plus 1 of beta equal twice bni of beta. If you do like that, how many scales can you put between 0 and L? Well, there is exactly log 2 of L of beta scales between 0 and distance L. Right? Because scales, the bubble diagram blows up, I mean, is multiplied by 2 every single time you change scales. So you have exactly log 2 of BL of beta scales. Now, imagine I didn't tell you yet how I do it, but imagine that the mixing is not where the problem is going to come from. Then I have log 2 of BL scales where on each scale I intersect with positive probability. So typically, I'm going to have very small probability of not intersecting constant log BL times in constant log BL scales. And if I take a small constant, the probability of not intersecting at least that many is going to be exponential in log BL, which means the power of BL, which is exactly going to give me the improved tree bound here. Okay, so this is maybe the only thing I'm going to mention on the general case, because this is kind of the nice part of the story for the general case, is that then intersecting in fewer than small c log 2 BL places will have probability smaller than, well, exponential of c prime c log 2 BL of beta. So something that is like BL of beta to some constant. And of course, if this is R, then the K was 2 to the R. So it also means that in our argument here, this will also be an inverse power of BL. Okay? So this is just to try to make you understand why you get the bubble diagram to some power. Was it, do you want more explanations on that, or was it sufficiently clear? I mean, clear is maybe a big word, but okay. So let's now state, and we will discuss the proof in the second part of the talk. Let's state the mixing property. And I should say that I'm hiding a lot of things under the carpet with the regularity assumption. There are many, many things to be done technically to go around it. But I should say that even in the case of regularity assumption, there is still this very nice mixing property to prove. And it's one of the main achievements of the paper. I also think it has probably applications in other contexts, and in particular in dimension 3. So what is going to be the lemma? So the mixing lemma, I'm going to state it even for one current. Okay. So I'm claiming that there exists a constant C such that for every n smaller than n to the C, so I want the inner and the outer annuli to, sizes to be very different. And E and F, depending on edges inside and outside, inside lambda n and outside lambda capital N respectively. Okay. Then I claim that the probability 0x of E intersected with F minus probability 0x of E probability 0x of F is smaller than constant over square root log capital N over N. Okay? And this is true for any x which is not in lambda n. So it's an additive mixing. It's not, we don't prove a ratio mixing. So it's not here, we don't manage to end up with the product of the probabilities. So it's not true that the probability of E intersected with F is within, is very close to probability of E, probability of F with an error which is of the order little of probability of E, probability of F. But it's still an additive mixing and it's going to be sufficient. Okay, let's stop here before we finish. Like that, we will finish with the proof of this mixing in the second part of the talk. Okay, do you have questions on this part of the talk? I apologize, I'm a little bit sick, and so my brain is not working completely full speed. So that's why I'm a little bit. So no question on this part? Okay, good. So let's make a 15-minute break and resume at 3.
Great, brilliant. Cool.
Perfect. Let me try to give you an idea first of the difficulty, where the difficulty come from. So you have 0, you have x, and you have an event that depends inside and an event that depends outside, okay? So the problem is going to come from the fact that the sources force the existence of a path from 0 to x. In fact, if you think about it and you will look not at 0x, but at empty set here, in fact, you would not even expect at criticality that with large probability you will have a single connection between the inner and the outer boxes. Because in some sense, there is no magnetization at criticality. And the currents are kind of telling you how much you are magnetized. For instance, if you think of, remember the sigma 0, sigma x squared is the probability that 0 is connected to x. So you see if sigma 0, sigma x tends to 0, then that means that the probability of 0 being connected to x tends to 0. Here it's between different annuli, so it's boxes to box, but you could believe me, and it's actually a statement, that the probability that there would be a connection between inside to outside would tend to 0. And then as soon as you don't have connections, you can start to use the mixing of the Ising model to prove mixing for the currents. So if you would be with sourceless, it would not be a big deal. The problem is that you are not with sourceless. You have sources 0 and x. So this forces the existence of a path. And this path, well, it could carry a lot of information from inside to outside. I always like to give two examples. The first example is trying to prove the mixing of the safe-forwarding walk. Try to prove even that safe-forwarding walk doesn't choose a direction and go in that direction. This is not very easy, and in dimension 4, definitely even harder. I mean, for the true random safe-forwarding walk, I mean, if you look at weakly, you have a renormalization technique, but for the true safe-forwarding walk. So having a mixing, trying to see that even if you just look at what happens in the 10 first steps, it's kind of disconnect and not related to what happens very far. It's a very difficult question. There is, if you don't like safe-forwarding walk, you may prefer percolation. And in percolation, there is this classical problem that consists in trying to construct the critical cluster condition on being infinite. It's called the incipient infinite cluster. So basically what you do is that you condition 0 to be connected to very large distance, to a point x very far, at PC. And you try to prove that when you send this point x to infinity, the thing converges to a certain measure. This is not known in dimensions 3, 4, 5, 6 for Bernoulli percolation. Actually, up to 9, it's not understood how you define this incipient infinite cluster. Well, here we are going to do something which is actually even stronger than that. It implies existence of the infinite of the incipient cluster for random currents, and in fact also for the random cluster model. But I will not add details on that. So we are trying to prove something delicate, and our enemy is the existence of this path from 0 to x, which is forced by the sources. So the idea is going to be the following. I'm going to make an even bigger drawing. The idea is going to be to try, so we have the small guy, we have the large. So E is in that, F is outside, X is there, 0 is here. We are going to take an intermediary annulus. And what we are going to try to do is try to go from one current with sources 0, one current with sources 0 and x, to transform it to have E occurring in a current with sources 0 and y, where y is going to be here, and an independent current F with sources y and x. So we are going to kind of want to split in two, in some sense, our event. And in order to do that, we are going to use what I like to call a kind of random resolution of identity. A random resolution of identity. Meaning what? Meaning a random variable x, which is almost 1. Okay? Yeah. So x is going to be the random variable that I'm going to define in a second. And the important thing is that this x, you should think of it as being 1. It's very close to 1. So what is this x? So let's define m, which is n to the 9 plus epsilon. I mean, 9 is just for technical reasons, but let's ignore that. And m, which is such that it's n to the 1 over 9 plus epsilon. Okay, so these are my I had lambda n, lambda capital N, and I introduce this lambda small m and lambda capital M, like that, okay? And now, let's look at the annuli here of size mi, which is 2 to the I m, okay? You look at the annuli up to m capital I, which is which is smaller than m and strictly larger, which is between m and m over 2. Okay. So you look at this I annuli. This time they are dyadic, and you define X to be the following. It's going to be the sum for I equal 1 to capital I, okay, of 1 over alpha I, I'm going to tell you what alpha I is in a second, times the sum for X, for Y, no, let's call it U maybe, U in the annulus of size mi plus 1 of indicator that 0 is connected to U. Okay? And alpha I is equal to I times the sum for U belonging to the annulus of sigma 0, sigma U, sigma V, sigma X, sigma 0, sigma X. Okay, why on earth do I define this thing? I define this because first lemma, expectation of X minus 1 squared is smaller than 1 over I. 1 over I. And if you think about it, the I is done in such a way here that I get something like log of capital N over N with some small constant. So I get something like that. Anyway, sorry, there is a big constant here. Okay. How many annuli do I have between small n and capital M? In the way I defined it, if I define n, which is much larger than n to the 9 plus epsilon squared. So let's say if I say, okay, take n larger than n to the 100, then I have logarithmically many scales. I mean, logarithm of capital N over small n, many scales between lambda m and lambda capital N. Okay, so that's the first lemma. And this lemma, I will prove it after. Notice just why did I introduce this thing here? This coefficient is exactly made in such a way that the expectation of X is 1. So then what I will need to prove is I will need to control the second moment. And I will do it, but I will do it after. Let me try, before proving this, let me try to conclude, okay? So proof of the proposition of the theorem. Was it a theorem? Yeah, proof of the theorem. By the way, in all these things, I'm not using dimension 4. I could do it in dimension 3 or in dimension 2, but there will be no interest. Okay, so what do I do? My plan is to understand this thing, right? And I want to compare it to probability of E, probability of F. But what I'm going to first do is I'm going to compare it to the following. N1, I mean X times indicator that N1 belongs to E inter F. Okay, I want to bound this. So how do I bound this? Well, I observe that here I could do that. It's exactly the same thing. And now I'm with the same measure. It's just that here I have x instead of having 1, but I know by the lemma that I'm very close to 1. So this whole thing is smaller or equal by Cauchy-Schwarz, an expectation of 0x empty set of x minus 1 squared. Ah, okay, I forgot to tell you what was the measure here. And therefore, we are in the sum of two currents. So here it's indicator in N1%. So it's smaller than this. This is just Cauchy-Schwarz. And if it's smaller than this, that means this is smaller than constant of a square root log capital N over N. So this is quite good because this is the square root that I was getting here. Okay? So what I would need to prove is I would need to prove that this thing is close to the product of the probabilities of being the product of the probabilities. So I want to prove the goal is to prove that this thing is roughly this, right? I would like to prove something like that. Okay, so let's look at this guy. And here, let's try to understand what is happening. So this is well, this is just the sum for u in the annulus M, capital M, of 1 over alpha I, where the I is, I mean, if you want, it would, I mean, you can also write it. Sum over u, sorry, in the annulus, of alpha u, which I will tell you what alpha u is, times probability 0x empty set of u is connected to 0 in N1% 2, and N1 belongs to E intersected with F. Okay? Where alpha u is something like 1 over alpha I, where u belongs to the annulus mi plus 1. Right? So what I do is I just take this. I mean, I'm looking at the expectation here. So it's a sum over every x. And for each x, I get 1 over alpha I, and I get indicator that 0 belongs to u. Okay? So now what I really want to be understanding is this type of quantity. U is connected to 0 in N1% 2, and N1 belongs to E intersected with F. Okay, so I have 0, I have X, and I have U. I know that the sum of the two currents has a connection from 0 to U, and here there is an event depending only on what is happening here, as there is an event depending only on what happens outside. So what I claim now is that I can do a switching. So imagine, assume, so recall the multigraph interpretation. Of currents. And let M be associated to the current N1% 2. Okay? So I claim with very large probability there exists K, which is a subset of M, such that the following occurs. First thing, I want the sources of K to be X and U. Okay, I want them to be these two guys. Second thing, I want that K doesn't intersect at all the small box. So K intersected with lambda n is empty. And I want, on the other hand, that M minus K intersected with ZD minus lambda capital N, or if you want, I want M restricted. Sorry. No, I don't understand why this idiot does this. M restricted to ZD minus lambda capital N is equal to K restricted to ZD minus lambda capital N. So I would like to find a current that has exactly sources. I mean, I want to find a subgraph that has exactly sources X and U, and somehow that is coinciding with M outside and doesn't intersect at all inside. I let you think about it. The only way this couldn't happen, the only way such a current doesn't exist, is if there exists two different clusters in the current, either there or there. If there is uniqueness of the current connecting this to, I mean, this small n to the small m and this capital M to the capital N, if there is uniqueness of the currents in both, I mean, of the clusters, then you can always find K. It's a little bit, it's a small combinatorial computation. It's not very difficult to see, but I mean, it's doable. Another way of seeing is that you can think, okay, let's remember, I mean, here I'm aware it's not a full proof. I'm trying to give you just an idea of the thing because, I mean, it's taking way more, I mean, the whole thing is taking way longer than I expected, and I'm even afraid not to be able to finish this proof. So I'm just giving you a hint, but maybe another way of seeing it is, if you want to find K, what would you do? Well, first you want a source from X to U. I mean, you want sources X and U. So you could start from X and start exploring the cluster, the current, until ideally you end up at U. Once you have done that, you have found a current with sources X and U. The problem is that this current, well, maybe it had already to go through this, through E. I claim that if there is uniqueness here, if there is uniqueness of the clusters crossing the annulus NM, you don't need, I mean, the red guy will not need to go through E. That's the first thing. Second thing is, once you have done that, so you have a current with sources X and U, it doesn't intersect lambda small n, very good. But you want it to be coinciding with M. So now you want somehow to peel off all the clusters connecting here to the outside in the current. But I told you, if you have no sources, the current has no reason to have long path crossings. But when I peeled off the red part from X to U, I removed the sources X, and the current I'm staying with is a current with sources 0 and U. There is no sources outside lambda M. And in this case, in fact, there is very small probability that you cannot find, I mean, that there is a loop in your current that would manage to make it through and cross the annulus between capital M and capital N. So here, I mean, I realize I'm doing a terrible job. I mean, that I'm aware, but I'm not sure how to make a better job. So bottom line, there is a very large probability of finding this K. Trust me and try to convince you of that exercise at home. There is a very large probability on this event to find this set. In fact, on this event, like this condition is exactly what you need to find this guy with large probability. And it's exactly why you introduce this U connected to 0. It's exactly to do that. Okay, so if you have this K, what you can do is you can run the same proof as for the switching lemma. You remember in the switching lemma, we were doing the symmetric difference with a path from 0, I mean, from a set K with sources A. We were making the symmetric difference in M and prove that you have as many configurations, blah, blah. Here, you can do the symmetric difference with this K. And when you do that, what you end up with is that you end up with the fact that the probability 0x empty set of U connected to 0 in N1 plus N2 and N1 belong to E intersected with F, you end up with the fact that this is sigma 0, sigma U, sigma X over sigma 0, sigma X. This type of quantities, we already saw them pretty often. They are just coming from the switching of the sources. And we are going to end up with 0U, UX. But you see, when you switch K, K is not intersecting lambda n, the small box. So when you are going to switch, if N1 was satisfying E, then after the switch, N1 is still satisfying E because you didn't change anything in the small box. On the other hand, K is equal to the whole current outside of lambda capital N. So when you switch outside of the box of size capital N, N1 becomes N2. So this you need to write it down. But what you end up with is that here you end up with N1 belongs to E and N2 belongs to F. So you see the switching by K allows you to change N1 to N2 here. But this is absolutely fantastic news because N1 and N2 are independent. So you end up with sigma 0, sigma U, sigma X divided by sigma 0, sigma X, and you end up with probability 0U of E times probability UX of F. When we discovered that, we were completely amazed in some sense. So you introduce this X, and it allows you to use the switching lemma to XOR, if you want, sorry, to make N1 belongs to F become N2 belongs to F. And then you have independence. So overall, what you end up with is that this guy that we started from is a product. So this guy, you can express it as expectation of 0x empty set, sorry, of X indicator of N1 belongs to E inter F. This is the sum over U of alpha U, sigma 0, sigma U, sigma X over sigma 0, sigma X. And then you add P0U of E, PUX of F. So let's call this maybe alpha tilde or beta of U. So what you end up with is that this is kind of an average of quantities that almost look like what we want, in the sense that it almost looks here like you have x and 0, but it's u instead. Okay? So overall, we just proved that P0x of E minus this sum of E inter F, sorry, we prove that this is smaller than constant over square root log n over capital N. It's almost what we wanted. Okay? So from there, it's just a collection of tricks to manage. Maybe let's call it beta ux here to recall. It's just a collection of tricks to prove that you can replace, in fact, here u by x and u by 0 here. So just to tell you a little bit, for instance, how you do, let me prove to you that, in fact, this quantity doesn't depend much on the endpoint, x. So E depends here, there is 0, there is a point x far away. I would like to prove this, that this is almost, this is almost the same. How do? I just pick that. I pick this and I apply it with f equals the full set. If f is equal to the full set, this is 1. And I can apply it for 0y, and I end up with this thing. Right? I just applied twice my inequality, once for once for 0x and once for 0y. But notice that here, this guy is exactly equal to this guy. It's the same guy. So if I can prove that this is almost this, then I'm done. But the beta, it's kind of expressed in terms of spin-spin correlations. And if you look at this alpha u, here it was expressed in terms of spin-spin correlation because it's something like that. So just if you have some kind of regularity of the spin-spin correlation, for instance, the gradient is much smaller than some kind of continuity, if you want, of the spin-spin correlations, then you can prove that beta ux is very close to beta uy. And this implies, so if beta ux is indeed very close to beta uy, then it implies that P0x of E is almost P0y of E. Okay? And trust me that it's an easy thing to get the regularity of the spin-spin correlation in terms of, in fact, you can get, I should write it, you can get this. So sigma 0, sigma x is smaller than 1 over x, sigma 0, sigma x, under regularity assumption. So that implies automatically that the beta ux is very close to beta uy. Okay? Okay, once you have that the P0x, so this is maybe, once you have that P0x of E is almost P0y of E, you can go back. So let's go back here. You can go back to this. And now, that's original. I don't know why it doesn't want to erase, but okay. If P0x is very close to P0y, here you can replace by P0x and remove the thing. So you end up with P0x E intersected with F minus P0x of the sum over U of beta ux Pux of F. But this, by applying the same formula, but this time for E, for E equal omega, this is just P0x of F. And you exactly end up with what you want. So bottom line, once you are there, you won. And bottom line before the bottom line is that you get there if you get this regularity lemma. So my goal now in the last 10 minutes is to try to tell you why you have this. Why is x very close to 1? Okay, first thing, maybe I should remind you what x is, and I should remind myself also what x is. So x is the sum over I equal 1 to capital I. There is a 1 over alpha I. I'm going to even write what it is. So it's 1 over I times the sum over U in the annulus mi plus 1 of sigma 0, sigma u, sigma x over sigma 0, sigma x. And then I have a sum, let me put v here, the sum over u in the annulus of indicators that 0 is connected to u in n1 plus n2. Okay, this was the definition. Okay. First thing, what is this? Well, this is this horrible sum, and here I have sum and probability of 0 connected to u, and this is probability in 0x empty set. So what is this? This is sigma 0, sigma u, sigma v over sigma 0, sigma x. This is the switching lemma. But then you see that this term summed is exactly canceling this thing. And then the sum over I, the sum over I here is canceling this. So this whole sum, the expectation is actually exactly equal to 1. That's why we introduce these coefficients here. These coefficients are exactly made for that. Okay, so the only thing I need to prove is that this thing is smaller than 1 plus constant over I. I don't know why I put absolute values. Okay, if I can prove that, I have that the second mode, I have the concentration. And this is going to follow from the fact, it's going to follow from the fact that when you fix I and j, okay, then if I look just at this sum here, if I look at sum over u in the annulus mi plus 1 and v in the annulus mj plus 1, that the probability that u and v are connected to 0 in n1 plus n2 I would like to prove that this is smaller than this quantity here for I times the quantity, the same quantity for j times the small error. So I want smaller than sum. I don't know why I didn't do that right away. Let's call this guy AI, okay? The annulus AI. So I want the sum for u in AI of probability, I mean, of sigma 0, sigma u, sigma x over sigma 0, sigma x, times the sum for v in aj of the same thing, times 1 plus big O of 1 over I minus j. Or even actually something like 2 to the I minus j. So what am I saying? I'm saying that if I and j are far away from each other, then the probability that u and v are connected to 0, so you will have 0 here, u here, and v much farther because they are in different scales. Well, in fact, it's almost, remember, this is nothing else than the probability 0x empty set of u connected to 0. And here it will be the same with v. So what I want to be proving is that if u and v are in different scales, then in fact the probability that they are both connected to 0 is roughly the same as the probability that the first is connected to 0 times the probability that the second is connected to 0. Okay? So roughly speaking, it's sufficient to prove that uv connected to 0 is like smaller than u connected to 0, v connected to 0, 1 plus an error, and that this error, you would like it to be like summable. But this, actually, we already kind of proved that because this thing we said was smaller than twice sigma 0, sigma u, sigma v, sigma v, sigma x divided by sigma 0, sigma x. Sorry, it was not twice. It's plus sigma 0, sigma v, sigma u, sigma x divided by sigma 0, sigma x. So here, if you think about it, and you want to compare that to sigma 0, sigma u, sigma x over sigma 0, sigma x times sigma 0, sigma v, sigma x divided by sigma 0, sigma x, right? Which would be, so this, sorry, this would be this, right? So we already mentioned, well, we already mentioned this inequality, and we want to bound the orange part by the yellow part. Okay, well, first thing, if if u and v are really in different scales, very different scales, so v is much farther than u, say, isn't one of the two terms much smaller than the other one? Because here, if you look at it, it's, so you have 0, you have u, so you are taking, here this guy is going to be kind of the spin between these two guys. Then this guy is the spin between these two guys, and then you, these two guys, this is a v, sorry. And then you have x here, and this guy is this spin correlation. But in the second term, 0v is this guy, and then vu is this guy again, and then you have this guy. But sigma 0, sigma v, this guy, is much smaller than this one, because u is much closer than v. So this second term here is much, is negligible. In fact, if you think about it, it's like something like, it's smaller than sigma 0, sigma v over sigma 0, sigma u times the first term. So 2 is smaller than this. So this is much, much smaller than 1. Did you understand why? I feel like, so you have U much closer than V. In one case, you do this, then this, then this. And in the other case, you do that times this, times this. So the second guy, you go very far away. At the first spin is way too small. So all of that to say that I can ignore this term. This term is negligible. Now, how do I compare the two terms? Well, here, let's remember that U and 0 are very close to each other and X is very far. So sigma U, sigma X here, this guy is extremely close to this guy by regularity. And this guy is extremely close to this guy. So the yellow term is really nothing more than sigma 0, sigma U times sigma 0, sigma V. But at the top, this guy is also very close to this guy, right? V is much farther than U, but it's still much closer than X. So in both cases, in fact, I had a lot of products, but only two guys were important because the other one, you can pair them in such a way that they give you 1. So the only that stays is sigma 0, sigma U for the first guy, and sigma U, sigma V. And in the second guy, you exactly get sigma U, sigma V, and sigma 0, sigma V. So we are almost there. The only difference is that here it's 0 instead of U. Well, I guess my pen is telling me that this is the end of the lecture. This is good timing. So what remains to prove is that this term here is close to this one. But it's the same thing. U is much closer to 0 than to V. So sigma U, sigma V is the same as sigma 0, sigma U, sigma V, sorry. So again, this guy is almost like this guy. So you really use the fact that guys are more and more farther away. So this correlation here is the same as this one. And this correlation is the same as this one. And in fact, even this correlation is the same as this one. So you use always this kind of regularity of the spin-spin correlations that I mentioned somewhere. There was a gradient somewhere. Yeah, it's here. This gradient assumption gives you automatically that all these orange terms are close to each other, and therefore you end up with the fact that the probabilities that U and V are very close, are connected to 0 is almost like the product of the probabilities. When U and V are very far from each other, I mean, are at different scales. So you see, morally speaking, what you did is that you use the regularity of the spin-spin to prove a decorrelation for these connection events, for U and V connected to 0. And then you use this to kind of decorrelate the events using the switching lemma. So it's not a very crystal clear proof, but I mean, it's a very powerful one. It's I mean, everything lies in this switching lemma. And to answer questions that were asked during the first lectures, I would really not know how to prove this mixing without the switching lemma. Many other things would work perfectly well because, in fact, the probability that U and V are on a random walk, like a Szymanczyk or a BFS random walk, you can also bound from above by terms that look like sigma 0, sigma U, sigma U, sigma V, sigma V, sigma X. But for the mixing, I have really no clue how to do it without the switching lemma. I hope I gave you an idea of what happened. it's not an easy proof. It's a paper which is rather dense. I realized it myself when I tried to present it, especially that it was the first time I was presenting this proof. But I hope I gave you a glimpse at the tools. Already there is this kind of thinking that, I mean, you need to keep in mind that you want to prove that you cannot have intersection without having many intersections. You prove that by saying that being an isolated intersection has small probability. How do you prove this? Exactly like for random walk, by proving that in each well-chosen annulus, you have positive probability of intersection, and that what happens in different annulus is roughly independent. And because these random currents are very far from being Markov processes or random walks or things like that, it doesn't come as a surprise that the very, very big step and the major difficulty in the paper is to handle mixing, proving that in different scales, things are roughly independent. And that is the type of things which I think was very far from being understood in the 80s, because it's a very probabilistic approach to the problem. It's not analysis hard, it's really probabilistic. Okay, I think I will definitely not have any time to tell you anything about four models, but you can go to the paper and look at the paper, and thank you very much for your attention.
We can unmute everyone and give a big go.
Thank you very much, and sorry for being a little bit down today. I realized that then my explanations were not so great, but didn't spend a very good night.
Well, then this is a good moment for any questions.
Yeah, are there questions?
Yeah, so you need this this mixing thing for when you have sources at x1 and x3, right? But you only so how does it extend? Because I didn't really, I mean, I'm still digesting the proof, but I don't think I see it.
You mean, I'm not sure I saw the question. So what is the...
When you stated this mixing condition, you had four currents, right?
Yes, that's an excellent question. So indeed, because you are doing an additive error, you cannot just say, well, you have mixing for each one of the currents. It's not, I mean, so you need to rerun the proof directly for four currents.
Yeah.
And you do it by defining not x, but a product of xi being an approximation of identity of one for the ith current. So you can easily guess that it's going to be even more messy. And here, remember that I did everything under the assumption that I have the regularity assumption. So the gradient estimates and so on, they would be working only in this context. So in the general context, you even need to define xi in a more complicated fashion to handle the non-regularity. But you are entirely right. As it is, it doesn't extend right away to four currents. You need to rerun the proof directly with four currents. Yeah, that's a very good question.
I have perhaps just an elementary culture question. So this argument for random walks, is that something classical in 4 dimensions? That they don't intersect?
No clue.
Sorry?
I have no clue. I'm guessing because I don't see how people would do it otherwise. But I never looked at the book on that. But I'm pretty sure it should look exactly the same. I mean, maybe they are like shortcuts, or maybe, but it's, if you want a kind of robust proof, I'm guessing people came up with exactly this type of argument.
Okay.
That's what I would guess. But I would not even be able to tell you if this is the case or not, because I never looked at the paper.
I see, okay.
Again, maybe in Lawler book it's done. I don't know. Maybe somebody in the audience knows and can pinpoint a place where it's done like that. Yeah. Would the many intersection property be helpful for the lower bound for the 2-point function? It's a good question. At least I don't really see directly how one would do that, because I don't even know how to do the lower bound for the 2-point function in the regime in D equal 5, where there the bubble diagram is even finite. You have no intersection with positive probability. So I'm not sure exactly where to. One thing which is certain is that there is another question which I find very interesting, and somehow I'm a little bit stuck on that, which is you can look at the susceptibility and how it blows up when beta tends to beta C. So in dimension 5 and more, it blows up like 1 over beta minus beta C. And this is actually fairly easy to get once you have all the random current technology. So if you want, go to Eisenman paper and look at the proof, because once you have the lectures from, the lecture from Wednesday, you basically have all the tools to understand the proof. I could almost have done it, but I mean, fortunately I didn't, because I would not have time to finish the proof of the mixing. But my point is now, that the reason why the susceptibility gives you what it gives you, let's see if my pen manages to, is that you prove that d over d beta of 1 over chi of beta, maybe with a minus to have something that is increasing, you prove that this is larger than probability, it's bounded, by probability, that if you start 2 currents at neighbors, they get far without intersecting. I mean, let's say it's roughly of this like that. So it's always smaller or equal to 1, and this gives you the mean field lower bound. And in dimension 5 and more, you can actually prove that this is larger than constant. 2 currents will have positive probability of not intersecting at all. In dimension 4, the many intersection property is kind of suggesting that they should intersect. So this probability, if you take points at distance L of each other, should decay, like 1 over log L to some power. And that is a very strong indication that chi of beta in 4D should have logarithmic corrections to the 1 over beta minus beta C. And that would be a very interesting thing to derive. Why didn't we derive it? What is missing? Because we exactly do that. We exactly look at intersection probabilities. Is that here, the intersection probability is really you take 0x and you take 1y, where 1 just denotes a vertex next to x. And you really look at the fact that the cluster in N1 plus N2 of 0 doesn't intersect the cluster in N1 plus N2 of 1. Okay? And you want to prove that this decays. So here you see, if you want to bound from below, you cannot do what we did, which was to add 2 sourceless currents and then use independence. So to answer your question, I think the many intersection property is going to be helpful for many other quantities, but probably you would need to derive it without referring to this additional sourceless currents, without doing the inequality that we did, this nasty lemma. Are there other questions?
Can I ask a fairly kind of, I don't know, like I guess it's a cultural question. So I want to know a little bit more about the role reflection positivity plays. So if I'm in dimension a billion, and you have the reg assumption for the 2-point function, then you don't need reflection positivity in your argument. Is that correct?
So if you are in dimension 1 million, you can use less expansion, and you have an estimate for the spin-spin correlation. So you would not need, under the regularity assumption, the regularity assumption, if you have it, whatever the way you get it, then you don't need reflection positivity after that.
Okay. And so, all right. So in dimension 4, you don't have the regularity assumption, and you don't have this So that means you also don't have this kind of this gradient thing you
Yeah, which is a nightmare.
Right. So then does reflection positivity play a role in deriving this or not?
Yes, yes, yes. So what you can prove typically is things like that. I'm going to give you an example. Let's call sigma n 0, 0 like that. So just a spin-spin correlation between 0 and n 0, 0. Call this un. Typically, you can prove that un plus 1 is smaller or equal to un. This is not already completely straightforward, so it's decreasing. Mm-hmm. This you can use reflection positivity to do that. And then you can also prove that this is larger than un, and here you get something like 1 over un over u, I mean, what should I put? Something like 1 minus 1 over n, so this is perfect, that's what you expect, to be dropping by 1 over n each time you go one step on the right. But what you get, unfortunately, is something like that, roughly speaking. So the problem you see is that as soon as un and u2n are roughly of the same order, you get a gradient estimate of 1 over n, which is perfect. But if you are exactly in a regime where you expect, I mean, you never expect that, but be the devil advocate and imagine, and imagine that u2n, I mean, un is really dropping a lot between un and u2n. Then, well, in this case, u2n, I mean, un divided by u2n may be very large, and you don't get any good control on the gradient. So in order to really manage to get things like that, we use reflection positivity all the time. We define even what we call regular scales, which are places where un doesn't drop too much, and we derive from reflection positivity information on that. And in the paper, there is one new thing which I think is a very useful property. It's a scale-to-scale infrared band, in some sense. It's kind of saying, so infrared band is saying sigma 0, sigma x is smaller than constant over x to the d minus 2. And roughly speaking, we prove something. It's a smeared version of it, but we roughly speaking prove sigma 0, sigma x divided by sigma 0, sigma y, with y smaller than x, smaller than constant y over x to the d minus 2. And this uses reflection positivity also. So reflection positivity is everywhere in our proof, which is not so, I mean, it's not so nice. At the same time, if you think of it from the point of view of Euclidean field theory, anyway you want to construct something with reflection positivity to be able to get something in quantum field theory. So it's annoying to use reflection positivity. I would definitely love to have an argument, a Gaussian domination that doesn't use reflection positivity. But as for now, we use it, and we really use it in many places.
Okay, thanks.
Are there any other questions? If not, let's thank Hugo again.
Thank you for staying with me.
Yeah, so many thanks, Hugo, for these fantastic lectures. And sorry, yeah, so just many thanks. And I stop recording you now. And should we just make a